When you hear the word cloud, what actually comes to mind?
Well, for most people, I imagine it's something entirely invisible.
Right, you probably picture something weightless,
Yeah.
just, software and algorithms sort of floating out there in the ether.
Yeah, doing whatever we ask of them on our phones. It is arguably one of the most successful pieces of marketing in human history
Oh, absolutely.
because it makes the digital world feel, entirely disconnected from the physical one. But if you look under the hood, the reality is entirely different.
Yeah, the cloud is highly intensely physical. And right now, according to the stack of technical sources we're looking at, that physical infrastructure is hitting a massive brick wall.
A literal physical wall, yeah.
Exactly. So, welcome to today's deep dive. We are exploring the silent physical hardware revolution happening right under our noses. Because if the industry doesn't completely tear up how power and data move, this entire AI boom you are seeing everywhere is going literally meltdown.
And that is not an exaggeration. I mean, the demand is currently pushing against the absolute boundaries of physics.
So let's set the baseline for you. What are we actually looking at here?
Well, foundries like TSMC, they're ramping their 3-nanometer chip output to 125,000 wafers a month by late 2024.
Which is huge.
Right, and they're already racing into 2-nanometer production.
Hmm.
At the same time, you've got memory giants like SK Hynix and Samsung in this brutal fight for dominance over HBM4.
Right, the next generation of high bandwidth memory. And when we talk about these advancements, 3 nanometer, 2 nanometer, we are talking about making the transistor so incredibly microscopic that you can pack billions more of them into the exact same physical space.
Correct. But to make these AI systems faster, they don't just shrink the transistors. They have to pack the separate chips, like the processor and the memory, closer and closer together.
They stack them in 3D, right?
Exactly. But doing that creates an astonishing thermal and electrical problem. Industry analysts actually call it the performance density trap.
Okay, let's unpack this trap. Because the way I'm reading it, it's basically like trying to park 100 high-performance sports car engines into a single one-car residential garage.
That's a great way to look at it.
Because, you don't just run out of physical space, you run out of ways to route the fuel to all of them. And critically, you run out of ways to cool them without, burning the entire neighborhood down.
That captures the bottleneck perfectly. And it's not some far-off future problem. The evolution of AI computing is driving data center rack power requirements up nearly 100-fold within a single decade.
Wait, 100-fold? That can't be right. In 10 years.
It is. Yeah, let's trace the progression from the sources. So in the Hopper era, think the NVIDIA H100 chip, a single server rack required about 32 kilowatts of power.
Okay, 32 kilowatts.
Then, with the Blackwell GB200 NVL72 generation, that demand jumped to somewhere between 100 and 120 kilowatts per rack.
Which, as I understand it, already required completely redesigning how these facilities are cooled.
It did. But the escalation curve gets much steeper. The upcoming Rubin Ultra platform, that's expected to exceed 646 kilowatts per rack.
Oh, wow.
And looking ahead to 2029 or 2030, the future Feynman platform projects over 1.5 megawatts for a single rack of servers.
Over a megawatt for one rack. That is mind-boggling. Most commercial buildings don't use a megawatt.
No, they don't.
So if we are pumping that much juice, the old wiring literally can't carry the load, right? You can't just pump a megawatt through the standard cables data centers have been using.
You absolutely cannot. And this is where we hit the physical limit of the traditional 54-volt or 48-volt direct current architectures.
Ones they've used for years.
Right. Data centers have relied on those voltages forever. But think about the basic physics of electricity,
Yeah.
Power equals voltage multiplied by current.
Right, the basic formula.
So if your power demand skyrockets to, say, 600 kilowatts, but you keep your voltage low at 54 volts, the current has to become astronomically high to compensate.
And high current is what requires thicker wires.
Exactly. Or, in this specific case, solid slabs of metal. To carry the current for a 600 kilowatt rack at 54 volts, you would need massive copper bus bars. We're talking weighing up to 200 kilograms just for one rack.
200 kilograms of copper. You'd essentially be turning the server rack into a copper mine.
Literally.
Just the sheer weight of that on a raised data center floor would be a structural nightmare.
And it takes up far too much physical compute space. Not to mention the traditional setup requires multiple stages of converting alternating current AC from the power grid into direct current DC and stepping it down incrementally.
Okay, and why is that bad?
Because every single time you run electricity through one of those conversion stages, you suffer a 1 to 2% efficiency loss.
Oh, let me guess. That lost 1 to 2% doesn't just disappear, it turns into heat.
It turns into pure heat.
Yeah.
When you are dealing with megawatts, those small percentage losses represent massive amounts of wasted energy,
Yeah.
and now you have to spend more energy to cool that heat down.
So if the old wiring literally can't carry the load without turning the server rack into a block of hot copper, what's the fix? I mean, the 54-volt architecture is basically dead on arrival for the next generation of AI.
It is. The industry is moving to an 800-volt direct current architecture. NVIDIA, for instance, has essentially cemented 800 VDC as the inevitable standard.
Right.
The fundamental shift here is that instead of multiple step-downs and conversions throughout the building, medium voltage AC from the grid is converted directly to 800-volt DC right at the data center campus entrance.
And just by switching to this 800-volt system, looking at the sources, the stats are incredible.
They really are.
Like, it increases power delivery capacity by 85% for the exact same wire size. It reduces copper usage by 45%. It improves the total cost of ownership by 30%. And it maximizes what the industry calls token efficiency.
Right, which is getting the absolute maximum AI output or tokens per watt of power consumed.
Right.
Because you are dramatically lowering the current, you can use much thinner, lighter cables.
It frees up space.
Exactly. You can pack far more computing power into the exact same physical footprint without that copper bottleneck.
But hold on, I have to push back here. Sending 800 volts of direct current straight into the server racks sounds intensely dangerous.
It is not a trivial thing.
I mean, 800 volts is lethal. If something shorts out, how do they actually manage that without blowing the billion-dollar chips to pieces or creating a massive fire hazard?
It's a critical engineering hurdle because you can't use traditional mechanical circuit breakers at 800 volts DC.
Why not?
Well, a mechanical breaker physically pulls metal contacts apart to stop the flow of electricity. At 800 volts DC, the electricity will literally arc. It will jump the gap through the air like a tiny lightning bolt, keeping the circuit alive and, causing a fire.
So what's the alternative then?
You manage it through a complete overhaul of the components. Specifically, they're utilizing solid-state transformers, or SSTs, and solid-state circuit breakers, SSCBs.
Solid state meaning no moving parts.
Exactly. Because they are solid-state, they use semiconductors to gate the electricity. They can detect and isolate an electrical fault in nanoseconds.
Nanoseconds. So the digital gate slams shut before the surge even has the physical time to travel down the wire and do damage.
Precisely. And to actually get that 800 volts down to a level the GPU can use, which is surprisingly less than 1 single volt, they deploy intermediate bus converters, or IBCs.
Okay, and where do those go?
These sit right near the processors and handle the final massive step down safely and efficiently in what they call last-inch power delivery.
This massive rewiring of the world's data centers isn't just an engineering marvel, though. It's a financial gold rush.
Oh, absolutely.
A recent Bank of America report projects this power shift as a $27 billion opportunity by 2030, just for the analog semiconductor industry.
It is a profound shift in value distribution. Texas Instruments currently leads that analog market, but projections show Infineon is positioned to gain the most market share.
Why Infineon specifically?
Because they have such a broad portfolio spanning this entire new power tree we're talking about. Analog Devices is also aggressively positioning itself. They recently bought a company called Empower, specifically because Empower specializes in that last-inch power delivery we just talked about.
And it's changing the physical materials we use, isn't it? Like, the processors themselves are still silicon, but for handling 800 volts, traditional silicon is actually failing?
It is. Silicon has a relatively narrow band gap. If you push 800 volts through a standard silicon-powered chip, the atoms literally can't hold on to their electrons.
They just break down.
Yeah, the current punches right through, causing massive leakage and heat. So to solve this, the industry is shifting to wide band gap materials like silicon carbide, or SiCl, and gallium nitride, JANA.
So silicon carbide rules the high voltage input stages because it can take the 800 volt punch without flinching. And then gallium nitride handles the high frequency switching right next to the compute units.
You've got it. They can handle the extreme electrical pressure and high frequency switching vastly better than silicon ever could.
Okay, so let's say we've done it. We've successfully delivered massive megawatt power to the chips using 800 volts, solid state breakers, and silicon carbide.
Sounds like a success.
We haven't melted the copper. But congratulations, we've just created a new, equally terrifying bottleneck.
Right.
Because now these chips are processing so much data, they're causing a digital traffic jam. They can't communicate fast enough over traditional copper wires without burning up.
Yeah, this is the data highway bottleneck. We've powered the brain, but the nervous system can't keep up. And this brings us to the next massive shift in the sources. Next generation co-packaged optics, or CPO.
The optical side of things.
Exactly. There's a fascinating academic paper published on Arxiv that outlines just how severe the specific bottleneck is.
Let's break down the scale of this traffic jam. Right now, a system like the NVIDIA DGX H100 needs 7.2 terabits per second of off-package bandwidth.
Yes.
That is a staggering amount of data trying to squeeze out of a chip through traditional electrical interconnects, the copper wires on the motherboard.
And those copper traces just can't meet the speed, energy efficiency, and bandwidth density requirements for the future. Pushing that much data through copy creates too much resistance, which, again, means heat.
Always comes back to heat.
Always. Co-packaged optics solves this by entirely replacing that copper with fiber optics, but bringing the lasers directly onto the chip package itself.
So instead of a fiber optic cable plugging into a big switch at the end of the server aisle, you are literally bringing the fiber optic strand right into the processor's house.
Yes, and they achieve these incredible speeds using wavelength division multiplexing, or WDM.
Okay, let's translate WDM for a second. It's essentially like using a prism, right?
Sort of, yeah.
Like instead of sending one signal down a fiber optic cable, you split the light into different colors, red, blue, green, and you send a different parallel stream of data on each color simultaneously down the exact same physical glass tube.
That is an excellent way to visualize it.
Yeah.
Using WDM, they can hit around 1 terabit per second per single fiber. But there's an insane energy hurdle here. It's not just about raw speed. The next generation of AI accelerators needs bandwidths over 10 terabits per second, but they absolutely must achieve it at an energy efficiency of sub 1 picojoule per bit.
Sub 1 picojoule. Okay, for context, today's advanced transceivers are sitting at around 6 picojoules per bit.
Right.
So they need to be 6 times more energy efficient while moving vastly more data. If they don't hit that sub 1 picojoule mark, does the laser just overheat and fail?
Essentially, yes.
Yeah.
Lasers are incredibly sensitive to heat, and processors are tiny ovens. Every single component in that optical link, from the clocking to the equalization circuitry, it all eats up precious power.
Right.
So engineering an optical transceiver that can sit millimeters away from a GPU and operate at sub 1 picojoule is one of the hardest materials science problems in the world right now.
But if they pull this off, the implications are wild. Here's where it gets really interesting to me. It's like replacing a congested highway full of delivery trucks with a network of instant light-speed pneumatic tubes that plug directly into the factories.
Yes.
If you have this network of light-speed glass tubes connecting everything, you don't just speed up the current system, you invent a completely new way for computers to work. The Arxiv paper describes this as disaggregated AI. What does that actually mean in practice?
Normally, co-packaged optics is just seen as an electro-optical bridge, a really fast but dumb pipe. But the paper suggests treating the CPO chip as a smart coprocessor.
Okay, so it has its own logic.
Exactly. In a disaggregated AI architecture, this smart optical chip can reach out and access the high bandwidth memory on a totally separate neighboring GPU without ever going through the central CPU.
Oh, wow. It's like realizing you don't need to route every single email through the CEO's desk for approval. The individual departments can finally just talk directly to each other instantly.
That's exactly it. It bypasses the CPU, it bypasses the crossbar, it bypasses the L2 caching. It's called direct memory access down to the package level.
And how fast are we talking?
The paper estimates this could drop the latency of accessing a neighboring GPU's memory to around 6 microseconds.
6 microseconds. That removes so much digital red tape.
It allows thousands of separate processors across an entire data center to act almost as one giant, unified brain, seamlessly sharing memory at the speed of light.
Okay, so we know the physics, we know the incredible tech being proposed, but let's bring it back to the real world. We know the theory, but who is actually building this complex ecosystem right now in 2026?
Well, if we look at the financial dispatches and market updates from May 2026, the numbers are pretty staggering. Take a company like Applied Optoelectronics, or AAOI.
Yeah, their projections are completely wild. Analysts are targeting over $1 billion in revenues for them in 2026. But by mid-2027, they are projecting $471 million per month in transceiver revenue.
Per month.
Yeah.
And a significant portion of that massive ramp-up is driven by the sheer desperation of the industry for their 800G and 1.6T lines.
The really fast optical lines?
Right. And they are actually expanding their U.S. manufacturing down in Texas, specifically to de-risk their supply chain from China, because these optical components are now viewed as critical infrastructure.
But AAOI isn't alone. They face incredibly fierce competition. Both Coherent and Lumentum just secured multi-billion-dollar purchase commitments directly from NVIDIA.
Yes, they did.
And NVIDIA even invested $2 billion directly into each of them to expand their manufacturing capacity. I mean, NVIDIA is essentially acting like a bank, funding its own suppliers, because running out of these optical parts is a bigger risk to them than just dropping $4 billion.
It really highlights how critical this optical infrastructure is to NVIDIA's roadmap. But, the macro environment still creates turbulence. We can see this in the Q1 2026 update from Sivers Semiconductors.
Right, Sivers is an interesting case. Looking at their report, you see a company in transition. On one hand, their opportunity pipeline grew by a massive 77%.
Reaching $799 million, heavily driven by photonics.
Yeah, but on the other hand, their actual Q1 revenue dropped 22% year over year.
Which seems contradictory, but Sivers explicitly points out in their filing that this specific Q1 dip was tied directly to a U.S. government shutdown that occurred in the fourth quarter of 2025. And the associated delays in defense budget approvals.
And just to pause here, we are looking strictly at the financial impact as stated in the source.
Right, absolutely.
We're not taking any political stance on the government shutdown itself. We just want to convey how the source explains the revenue drop.
Exactly, because the demand didn't vanish. The pipeline is fully intact, but the actual revenue realization was just pushed into the second half of 2026 due to those federal budget delays.
It's a perfect example of how macro-level government operations can create immediate ripples in the most advanced tech supply chains in the world. Speaking of supply chains, the forums and industry whispers give us a peek behind the curtain at who is doing the really heavy lifting that doesn't make the front page news.
Foxconn is a prime example there. They recently announced they are targeting the third quarter of 2026 for mass production of their CPO switches, aiming for 10,000 units.
But the forum rumors point out that Foxconn can't do it alone. A company called Foci might actually be a major bottleneck as they supply the vital passive components.
And then there's the massive packaging challenge.
Right, because attaching microscopic glass fibers to hot silicon isn't like, snapping Lego bricks together. It requires alignment at the microscopic level.
It's incredibly delicate.
And the notes show that while Foxconn gets all the headline orders for CPO and photonics from NVIDIA, it's actually a company called Shunson, often operating completely under the radar, that does the crucial microscopic packaging and testing for those optical orders.
The broader market doesn't always catch these subsidiary dependencies, but Shunson's ability to perfectly align those fibers is the bedrock of the actual manufacturing process.
It really is.
And we shouldn't overlook XFAB either. They're positioned at a $1.5 billion market cap to be a central beneficiary of the EU CHIPS Act, specifically for their silicon photonics capabilities.
It's a massive, highly delicate global web of foundries, packagers, and material science experts working furiously.
Yeah.
So what does this all mean for you listening to this right now?
That's the big question.
If you are trying to understand where the AI revolution goes next, you cannot just look at the software hype. You have to look at the physical realities of the supply chain.
Because the algorithms and the software interfaces, they get all the glory, but the hardware has to obey the laws of thermodynamics.
Exactly. The companies that figure out how to stop the silicon from leaking electrons at 800 volts, how to align microscopic glass tubes to bypass the CPU, and how to deliver megawatts of power without burning the building down, those are the companies actually making the AI future possible.
And if we connect all of this to the bigger picture, it raises an incredibly important, almost provocative question to end on.
Oh.
If rack power demands are truly scaling to 1.5 megawatts with the Feynman platform, and data center architectures are shifting to campus-level 800-volt direct current microgrids utilizing solid-state breakers,
Yeah.
we have to ask ourselves, are the data centers of the 2030s really just IT facilities anymore? Or are we, in essence, building specialized hyperdense power plants where the byproduct just happens to be artificial intelligence?
Wow. A power plant where the byproduct is intelligence. That completely flips how you think about it.
It really blurs the line.
It's not a computer you plug into the grid. It's the power grid itself thinking.
The physical infrastructure and the digital output are becoming entirely inseparable.
That is a fascinating thought to leave on. Thank you so much for joining us on this deep dive. Next time you use an AI on your phone, don't just think of the invisible cloud floating weightlessly above you. Think of the 800 volts of direct current, the 200 kilograms of copper being replaced by silicon carbide, and the light-speed optical glass making it all happen. The cloud isn't floating, it's fighting not to melt. We'll see you next time.